So let's start. Good afternoon, everyone. Thank you for making time. Please come in. It is my distinct pleasure to introduce to you Dr. Niccolo Maffezzoli. Nico is a visiting scientist with us. He comes here with his own funding, a Marie Curie fellowship. But he got his master's in nuclear and particle physics in Milan, has a PhD and did a postdoc at the Center for Ice and Climate in Copenhagen, Denmark. He used to work on continuous flow analysis systems and coupled plasma mass spectrometry for the detection of chemical traces in ice cores, and that was for past sea ice reconstructions. He continued this research with the Italian National Research Council at the University of Venice. And there he started also getting funded through a Marie Curie fellowship. That's a European fellowship, very prestigious. And worked with the University of Venice and University of Bergen on a project on artificial intelligence techniques applied to ice core analysis. He was the PI of IceNet project on glacier modeling using deep neural networks between 22 and 23, and he visited us in this aspect in preparation for his visit now. And since October, he is a PI for a Skynet program. Yes, those of you who know the reference will know that this person is working for Skynet on artificial intelligence, and we're here to hear more about it. Thank you.
Thanks. Thanks, Ben, for the introduction. And yeah, my name is Niccolo, and today I'll work a bit on the project that brought me here, which is some AI methodologies applied to glacier ice volume estimates. So I'd like to thank my sponsors, so Climate Change AI Foundation and the Marie Curie program. And I'd also want to thank my friends and colleagues, both here and abroad. And so this work is a joint effort. Here at UCI, I work with Eric Rignot, and I work with different people also in Europe. So the research question is this one. So satellites give us a lot of information about the Earth's surface and the features of the surface, but to which extent can we use such information to extract some fingerprint of what is below the surface? And in my particular case, I'm interested in glacier thickness. So how thick is the glaciers in general. So this talk is generally split in two parts according to the two paradigms on which the problem was framed on, a regression problem and an imaging painting problem. So I'll try to kind of have an approach that may provide some clues and hints that may be general also to other Earth system science problems. Maybe you have also some data sets, and maybe some of what I say may be also relevant to your particular case. So we have a problem, which is we want to estimate the ice thickness for Earth glaciers. Essentially, we want to estimate the function, which is h, is a function of a point inside a glacier, and is also a function of some data that we may have available. And in general, the function may be parameterized by a vector of some parameters theta. So we want to estimate this function. Kind of the glaciological community has collected the information on glaciers. So we know, we keep track of glaciers, and we know where glaciers are. And we kind of digitalized all the perimeters of each glacier. And we categorized these glaciers into an inventory, which is called Randolph Glacier Inventory, currently version 6, or actually 7. There was a new one that came out 2 months ago. Because glaciers change, so we keep track of them in both a number and also shape. So we have this inventory, and you can see all the glaciers here, including in the 2 regions of Greenland and Antarctica, so in the peripheries of these 2 ice sheets, and all the regions included between Greenland and Antarctica. There are in total 19 regions, and the total glacier count is above 200,000. So this gives you a bit of numbers of how many glaciers we have, and we're interested in estimating the thickness. The thickness is important. The thickness distribution means the thickness in space. That can give us the possibility to calculate also the volume. And volume is important for, freshwater resources, sea level rise, etc. What is the state of the art, or what do we know about glacier thickness? We do have measurements, and measurements are local measurements of ice thickness. We have a very important database called Glacier Thickness Database, containing 3.8 million thickness measurements, but over only 3,000 glaciers. So it's a very sparse data set. And where we don't have measurements, we have modeling efforts. And these are 2 very important modeling efforts for almost all of the glaciers worldwide. The first one by Farinotti et al. Is an ensemble of up to 5 models, while the second modeling efforts by Milan et al. Is one model, shallow ice approximation. So we have also these 2 models, modeling solutions. This table is from the publication by Milan et al. And shows for each region here. The last column is the regional difference in percentage between the total ice volume predicted by them and predicted by Farinotti et al. So it's the percentage difference between the 2 modeling solutions. And some regions, the match is fairly good, but we also have some mismatch. So that gives us also the motivation to explore other possible solutions to this problem. So in machine learning, in general, any type of data is good. And in general, we may use different data sets produced in relation to glacier and glacier thickness by any means. In general, they can be produced by space missions, so remote sensing, airborne, or in situ measurement campaigns. Some data are direct ice thickness measurements, so this is our ground truth, and some data are related to ice thickness, and they are informative of ice thickness. Some features, I'm gonna use the term feature or data a bit exchangeably, but some features are local and some are like spatially integrated glacier information, like, for example, the area of a glacier. And we call this set of features as data, we refer to as data, and that may be also an elevation map above the Himalayas, surface ice velocity, the number of days above melting during summer. In general, all the data that you may think relevant to the problem may be worth testing. And in general, the approach in machine learning is the more the better. And you can always, in some ways it's more difficult, but test how important some variable, some data is. And we use a data-driven approach, and we ask ourselves how much information can be gained from this data, how much can we squeeze, and what are the tools for that. And we're interested in a generative model, so we are interested in producing information, and in this case we want to also produce the ice thickness. So we are kind of generative AI is we are not only interested in classifying photos in terms of maybe some classes, but we want to generate information. So we want a generative local model that may work with some limitations, but on each point inside the glacier. So the first approach is regression. So this is the first part of the talk. We can create a training data set of points, and with the following features. So we created this training data set from measurements and features from the Canadian Arctic, from Svalbard, Scandinavia, and Central Europe. And you can see 15 features and the ground truth. So the ground truth is our target, and is the ice thickness measurement. So we know some ice thickness measurements, and we want to leverage on this and building a model that connects, like a functional form that connects this set of features to the thickness. Once we have that model, we may be able to generalize and use this model elsewhere where we do not have thickness measurements. So among the features, there is the area of the glacier, the slope in terms of X and Y axis, the average slope of the glacier, the elevation of each point, and then the glacier minimum, maximum, and average elevation, the elevation of the point with respect to the glacier minimum, essentially is the elevation minus Z mean, the distance of each point to the glacier borders, and then the velocity, the surface ice velocity. We may also have the length of the glacier. It's kind of fuzzy defined, but if you think that a glacier may be elongated, that's the L max, the maximum length of the glacier. And then we also inject the information about the region. So that's which region is the measurement taken from, the Arctic, the Europe. Maybe the model cares for this feature, maybe it does not. And then we have our ground truth, which is the ice thickness. And so we have our training data that consists of the metadata, the features, and our ground truth. So we call it a supervised approach because in this model we know the ground truth. So this is just an example of how one particular feature was computed, which is the distance of any point. Here you see one point in red to the glacier borders. And it's a bit complicated because the glacier borders also include what are called nunataks, so portions of the glaciers that are inside the glacier itself that are deglaciated. So we kind of believe that the distance of the point to the borders should account for nunataks as well. So in general, a lot of effort goes into building the training data set, and that is kind of half of the job. And because the model kind of learns from the training data, so whatever feature you put in the model should be representative of, informative of the target that you're looking for. Then we also thought, okay, but what's the geometry of the problem here? Because we have kind of a spatial representation of the features, which is not trivial. Here is, I show the velocity, which is one of the features, the velocity along x, of the points. And you can see that the points are located along the tracks of the measurements. Sometimes is snowmobile tracks, sometimes is airplanes. And we kind of thought that this geometry is informative, or maybe informative of the problem. And is there a way to account for that? Because there may be also valuable information in the data structure. And how do we incorporate it? One other thing is always the risk of overfitting in case of a data set. So in the plot on the left, there are around 20,000 points in the blob below. So if you have a model that learns from a specific part of the data, because the data there are very, very dense, then you may end up with a model that is not really able to generalize to other space of the features. So one way to accommodate for that is just to make a spatial grid and average all of the points in that blob. So this is just a concept of overfitting, and technically it's like you have a skewed distribution of some particular feature, and we kept this in mind because, and in the end we decided to grid this particular feature. So in general, if you have a complicated geometry, you may want to move from a simpler tabular representation to graphs. So graphs are a kind of universal representation of data and consists of nodes and edges. The nodes are typically associated with data, while the edges represent the relationships between the nodes, the data. In our case, the nodes are our lat-long points where we have the measurements. And so for each node, we have a feature vector, x, these 15 numbers. And then we have the connection between the nodes, which is represented in the adjacency matrix. So you must think that, so in our particular case, we define this matrix as being, so the connections as being one, whether the two nodes are closer than 3 kilometers, while the connection is lost if the distance between the nodes is greater than 3 kilometers. And that's a choice. So we define such geometry, and we also weight the connection between the nodes, and we use a weight which is 1 over the distance. So two nodes talk to each other a lot if they are close, and the connection is weaker and weaker as the distance between the nodes move further away. And the connection is totally lost if the 2 points are further away than 3 kilometers. So, and we also use an undirected graph. So in general, the connection may include a direction. In our case, we don't use that direction. And why are we using the graph? Well, conceptually, we want the model to consider that if you do have a feature, a space on a glacier, maybe points that are closer together should talk to each other because they contain a similar information. So that's why we're moving actually to graph. And we know that neural networks has been successfully applied in many cases of structured data. Images is the first example. Graph neural networks are an extension of neural networks that work on graph data. And with GNN, the concept of convolution moves from an operation which is done on a structured grid, like this moving filter that makes the inner product with a structured grid, to an operator that accounts for the interconnection between the nodes. So we use a graph convolutional network to solve our regression problem. And it's a node regression because we want to estimate the thickness at each node of our graph. So we construct our graph with 3,000 nodes and 3 million edges, and each node is associated with 15 features, and we use these edge weights, the inverse of their distance. In the GCN, the architecture behind is a multi-layer perceptron with 4 layers, with that amount of neurons for each of the 4 layers. And so in neural networks, there is a forward pass, and the data is injected from the left, and the data is machined by the different layers until you have an output. In our case, the output is one number, is the ice thickness. This formula represents how the embeddings, so the feature vector in one layer, is passed to the next layer. So essentially, for node I, so X with I, the embedding, the feature representation for the next layer K+1 is an average of all the neighbors J of node I, all their embeddings and their weights, their connections. So you make this average of the neighbors. You average the embeddings of the neighbors weighted by the relative strength, and the weighted average is taken from the layer of the neural network to give the next embedding. So this is how the embeddings are transformed from layer K to layer K+1. You can see that in a normal neural network, you don't have this weighted average. So you just take the embeddings and you multiply the embeddings with the layer W. Here you have this weighted average that accounts for all the connections of the central node. Then you also normalize, you use an activating function, but the take-home message here is that you use the connections to make this weighted average between the central node and all the neighbors. So we train this with a squared loss, as is usually done in regression problems. And like all machine learning programs, you calculate the derivative of the loss function to the weights, and you optimize the weights in a standard gradient descent, and this whole machinery is the same. So we train this, and then you test it, and we test the model on 1,800 points from dispersed in glaciers in Svalbard, which is the region number 7, and we compare our model output with the truth. So on the x-axis is the ground truth, and on the y-axis is the model solution. Our model is in blue, and the other two models from Milan and Farinotti are in red. And on the right is the distribution of the residuals, so the difference between the model and the ground truth. And the model of Farinotti works very well in this region, and our modeling result is close to Milan, and the standard deviation of the residual distribution is a bit higher in our case. So how do the solution look spatially if you were to plot all the thickness predictions? You end up with this plot. So on the top left, you have the ground truth. Middle top is our solution. Top right is Milan, and bottom left is Farinotti, along with the difference between our solution and the ground truth, and the difference between the ground truth and Farinotti. You see here it's all white because you can't really see any difference between Farinotti and the ground truth. Farinotti works very well. So we have some response from the model. I'd say it's not perfect. Also the spatial consistency of the solution we're interested in. So this is some part of our work. I'd say it's work in progress. It's not really easy to train a GCN, but we have some base level to work on. Another type of method that can be applied to regression is a more standard approach using decision trees. A decision tree, an example is here. So you have many nodes. In each node you have a decision to make on a threshold, on some feature. So X are the features, X0, X1, X2, Xn are the features, and some data agree to this selection, some do not agree, so you end up with branches, and you may have other nodes, and in the end you have the leaf node. In the leaf node you have your result. And the algorithm determines how many splits there are, what features should be taken into consideration, and which threshold values are to be put in place, and does that by splitting the data recursively and kind of evaluating a metric each time, and maybe the variance. So it's a kind of a more traditional machine learning method, and we train this. This is much faster to train. Again, we train on roughly 28,000 points, and we test the model on the remaining roughly 2,000 points. So it's a standard procedure is that you have your training data, you split the training data, and you kept the bulk, the majority of the training data to train the model, and you reserve the small part to test the model. But this time we do this cross-validation 1,000 times, and each time we randomize which points fall in the training set and which points fall in the test set. So this is a kind of more robust test that we are doing compared to the one single run that I showed you before with the GCN. And again, the training data are from 4 particular regions, not all of the 19. Why 4? Because we have the ground truth more easily accessible from these 4 regions, but that may be also be extended to other regions. And this table shows the residual standard deviation and the median of the distribution. So our model is roughly the same, in the same kind of uncertainty band compared to Milano and Farinotti. Also the bias is very close to 0. So we want essentially the model not to be biased in either positive or negative predictions. Again, we can evaluate how the solution is spatially, and again, the top left is the ground truth, and then moving towards the right, we have our solution, Milan solution, and in the bottom row, Farinotti, and then the ground truth minus our solution in percentage this time, and the difference between the ground truth and Farinotti on the bottom right. And this is, I believe, from, it's a glacier from the Canadian Arctic. And we see that the model does a fairly good job. There is some coherence, some spatial coherence in the solution. And this is another prediction on another glacier. I believe is also, yes, from the Canadian Arctic. And then a cool thing is that we can also evaluate which features are important for the model. And so this is a plot of feature importance. The most important features is the distance from the point to the glacier edges, including the nunatak. So that's a very informative feature. Then the elevation, the area, the kind of the maximum length of the glacier. And the bottom, I'm very interested in the bottom features that are the region. So according to this result, the model doesn't care whether the point was taken from Svalbard or from Central Europe. And also the local slope and the velocity are less important. And that's a bit puzzling because one of the 2 models, Milan's models, is essentially built from velocity and slope. So that's a bit puzzling. We ask ourselves, why are these variables less important in our model, and whether we could squeeze more information from them. So we have different possible answers to this. One of the simplest is just we calculated them erroneously. So that's also a way to check by making a feature plot what's going on with the. It's a way to debug the model in a way. Okay, but we want a generative model, so we are interested in predicting the ice thickness in every point inside the glacier. So we go back to square one and we calculate the features. So the set of feature, which I call here X inference, for any point inside the glacier. So we calculate all the 15 features because we want essentially to build a complete prediction of ice thickness inside the glacier. And we do that and using a decision tree in this case, and our solution is on the left, the central plot is Milan, and on the right Farinotti. We can see some similarities. The bottom left area and the bottom area are kind of a bit closer to Farinotti, then we don't see this higher ice thickness predicted in both models there. So we're kind of evaluating where we are firing, why, what are the differences, what kind of structures our model can see, can understand. This is another prediction from Central Europe. Again, our prediction on the left, and then Milan and Farinotti. And then there is another example. This is the Aletsch Glacier, the biggest glacier in Central Europe. It's in Switzerland. And we see that there are a lot of features in our model. Although the decision tree is a very local model, in a way the points do not talk to each other. Unlike the GCN that we are trying to train, the decision trees do not, the training points do not talk to each other. But despite this, we can see that there is a remarkable, I think, spatial pattern. So that brings me to the end, some conclusion on the first part. A regression model can be built on this set of features, and in the decision tree we commit an error which is on average 90 meters with a bias consistent with 0. The model is trained on these 4 particular regions. So one of the main questions that we have is whether we can generalize using this model outside this training domain. Also, the spatial consistency of the solution. We are trying to understand what types of features we are building, and if it's compliant with physics. That's a big question. Also, can we improve? Can we maybe use other additional features that may improve the error? And what insights, what types of structure is the model able to predict? So some benefits and potential. Kind of a neural network allows more flexibility, a more elaborate architecture, and also able to include existing solution if you wish. On the other hand, like a more standard machine learning model is a bit more rigid, but is typically easier to train and also to understand. So these are some benefits of both of these methods. Yeah.
Can you say a bit more about how the Milan and Farinotti methods work? What assumptions are made?
Yeah, so Milan, so Farinotti model is an ensemble of up to 5 models, and they're kind of fit to the data in a way. So the way they average, they make a weighted average of all these up to 5 model solutions. Some work in some regions, some other work in other regions, and they kind of combine the ensemble of their models.
They're physical inverse models, or they're purely statistical? Or?
Yeah, both, as far as I remember, both. And Milan's model solution is a shallow ice approximation. So essentially, they get slope, they get surface velocity, and they use those 2 ingredients plus some hyperparameters which they tune to the measurements. I'm thinking about the beta, which controls the ratio between the surface and the bottom speed. So they model that, and also an upper parameter A. They kind of fit, they invert the equation where they have the, I think, ice thickness measurements, and they make a fit to get this other hyperparameter. So this other approach is a bit unsupervised, I would say. So we know that mountains grow on, glaciers grow on a repetitive pattern of the crust elevation and kind of fractal-like structure. And we thought we could kind of leverage on this. So we define DEM as the elevation of the surface above the ice, if we have a glacier. And we define the bed as the elevation of the glacier bedrock. And if we could master this repetitive structure, we could be able to model the bedrock elevation. If we could model the bedrock elevation, then we just subtract the DEM. The DEM is given from satellite products, is a satellite product. We just subtract the bedrock from the DEM and we get the thickness distribution. And we want to model the bed using our neural network. And the problem is framed in an imaging painting problem. So imaging painting is the task of reconstructing missing information inside the image. And neural networks are the state-of-the-art technique for such a task. So essentially you have some missing information on the left and then the neural network prediction in the middle and the ground truth on the right. So, okay, imaging painting may be also useful for other applications like object removal, image restoration, for example. And one way to solve this imaging painting problem is using a generative adversarial network. This is a sketch of how GAN is used in the realm of imaging painting. So GAN is made out of two neural networks, the generator and the discriminator. The generator is the forger and the discriminator is the police. The objective of the generator is to create realistic images, and the task of the discriminator is to flag them as fake. So in this case, we have the generator. Here is the green network that produces a fake image, and the discriminator accepts both the fake images from the generator and also the real images from the training dataset. And the job of the discriminator is to flag the real images as true and to flag the created but realistic images from the generator as fake. So essentially it's a min-max problem, and they try to either minimize or maximize this target function. So essentially the discriminator wants to maximize it, so wants to maximize its output when fed with real data, and wants to minimize its output when fed from fake images from the generator. While the generator wants the discriminator to flag its own images as true. So it's a min-max problem. You can see it's kind of difficult to train, and essentially they move towards an equilibrium in which they do not improve anymore. So we use this model. The generator here is made out of two branches in a encoder-decoder kind of fashion, while the discriminator network is this one below. The imaging painting problem is essentially works in masking a part of the DEM. So you get rid of some information in the DEM and you try to in-paint information inside. So the goal is to develop a model able to reconstruct the bedrock topography over mountain regions. And then we can train the model. Once we have the trained model, we can predict the bedrock at inference time below glaciers, hence infer the thickness distribution by the difference. And so we have to create a training data. We take a DEM region and we extract patches of elevation over essentially over mountains, but we do not want to sample the glaciers, of course. So we stay kind of close to the glaciers, and we create patches by enforcing some constraints. The first constraint is that the patch should exceed some elevation threshold. The second constraint is that we do not want to sample the glaciers, and we kind of allow some degree of overlap between created patches. This is how a training dataset looks like. We have images 256 times 256. We can sample everywhere, but the Himalayas offer a great amount of space from which to sample. So we have a training dataset from the Himalayas that exceed 1 million images. That may be a bias, of course. Also, how you mask the information on the images is a very important variable, both in terms of shape and size, because the shape and the size of the mask kind of drive what features the model is learning. This model is much bigger, trains one epoch in roughly 10 hours. So this is a kind of a big model. And this represents some training images and how the model reconstruct the missing information. So the mask is actually encompassed between two black lines. For example, in this top example, you have the original DEM and how the model in-paints information inside the mask. And you can see that at iteration 5000, it's not really great. And as the model progresses, you see some very blurred patches, and as the model progresses, it improves its reconstructions. This iteration 81,000, you can see you still have a lot of differences and blurriness in the prediction, but it improves, and this is iteration 96,000. You can see, for example, here you have some very weird artifacts towards the edges of the patch. And essentially, once you have your trained model, you apply the model to patches with glaciers inside. So in this case, you have one glacier here in the middle, but it happens most of the times that you don't have isolated glaciers in the patch. You also have a lot of neighboring glaciers. And so this is a bit of a problem, because the information that the model considers is kind of much reduced by the presence also from other glaciers. So also the size of glaciers is a big thing, because in this case we have roughly 50% of the information which is essentially covered. And then we deploy the model, and this is very, very preliminary stuff, but this is some comments I made below. So you have the original DEM with the mask here. So these are all glaciers in kind of gray. And this is how the model predicts the bedrock. And from the prediction, then you subtract the prediction from the DEM, you can calculate the ice thickness distribution. And on the bottom right is the Farinotti solution. So one comment is that if you can also provide slope maps as input to the model, and the model considers the slope maps very much in making the prediction. You can see that the prediction kind of follows the surface slope. This is another example of another glacier. Again, we are too early in the study to consider the ice thickness distribution. We are just trying to understand what the model does, and there are weird discontinuities in the prediction of the unpainted solution, and that kind of make us think that the gun loss needs some tuning, because we don't want discontinuities in the. We found discontinuities a bit weird. Another problem is that, again, is there enough information for the model to unpaint? You can see here most of the more than 70% of this patch is covered by glaciers. So that of course reduces the amount of information available from the model to unpaint. So this is another glacier. And the worst possible solution is this one. There is nothing that prevents the model to predict a bedrock which is above the surface. So this is, I'd say, our biggest problem is this one. We predict actually a non-physical solution, an ice thickness which is negative. So we are trying to understand how to solve all these issues, but this is the kind of the supervised approach. So some conclusions. So this model is exposed and can learn from, theoretically, from a lot of data. Also, a benefit of this approach is that you can stack many products as input to the model. You can feed the model with the DEM map, but also with the slope map. And that is may be considered by the model and beneficial for the prediction. The biggest challenge is, of course, the non-physical solution. This is a kind of joke. The experimental physicist says we beat the net with a stick and penalize more for above ground predictions. And the computer scientist says, yes, I'll do it, a squared loss. But then the theoretical physicist said, that's not elegant, forget it. That kind of conversation was a real conversation. So another challenge is that this is a big model, it's difficult to optimize, lots of hyperparameters, and we are thinking about a scale problem. I mean, the glaciers may be very small, medium, big, so that creates actually a scale problem, we think. And other questions that we have is what features is the model learning? Where can we use such model? The required accuracy here is very high because we are predicting elevation. So if you have an ice thickness of 70 meters in Europe, you are predicting a glacial bedrock which is above 2,000 meters maybe. the error you can make is very low. Also, we are playing a lot with mask size, different shapes, and maybe different masks are required in different regions. So these are some of the challenges that we are facing. That's the last remark on some improvements. We're working towards combining the two models and have the regression model suggest some predictions for the in-painting problem. And then another approach, this is another approach, is whether your problem has a partial differential equation, so the problem is described, the physics is described by a PDE. You can solve a PDE using a neural network. And in this framework is one of the cool thing is that you can also use data to solve the PDE. So that's I think very beneficial, and the data can be the data themselves where you have data, or they can be predictions from another network. So that's the end. Thanks a lot for your attention, and I'm waiting for questions.
So thank you. Just for the people online, if you have questions, please type them in the chat or let us know, raise your hand. I will monitor the chat. And for the discussion in the room, Nico, if you could please repeat the question. So
Yes.
Summarize so that people can actually hear what the question was. Thank you. Any questions?
Say again the question, sorry? So we used those 15 features, and right now we are using those 15 features, although we are very much working in understanding maybe some are not relevant, or actually the one is really not relevant, and maybe some other features can be machined in a way that the model considers them to be more informative. Yeah, so we are kind of working on the features a lot. Yes. How many? Sorry. How many epochs?
Sorry, just repeat the question for the audience online.
Yeah, so the question is how many epochs did we use to train the GCN? How many epochs? The number of epochs was 30,000. Yes, I think at about 20,000, after about 20,000 epochs, the model learns marginally. Yep.
I have a related question about the feature you include in the model. Do you think including the not relevant features or the skill of your model? If you are removing those features, you get better skill, or it doesn't matter?
So the question is whether if some features are removed, what's the change in prediction error? We are working on that, and so one feature, which is the region, is just a float. It's a number. That's, as far as we found, completely irrelevant. But other features may be less relevant. We don't really know. I don't have a straightforward answer. yeah, we are also working towards creating a new features, or just maybe using the available features in a different way. One can, for example, think about dividing, I don't know, dividing the surface speed by the slope to the power of something. For example, the shallow ice approximation, we could kind of mimic the shallow ice approximation in a way, and maybe the model improves, maybe not, or calculating the gradients of the velocity, maybe informative.
I was wondering if those other models, parameters from Milan or
Yes, so we thought about injecting Milan's solution as a feature. I think we tried it, but so far we are sticking with, because we also want to compare with Milan, so we don't want to use their solution in a way, but we thought about that, and that is easier to do with a neural network than with a decision tree structure. But yes, we also thought about exotic things like having a branch of the neural network compute an ice thickness prediction, and then training with the residual from our solution and Farinotti's solution. So essentially kind of correcting Farinotti's or Milan solutions. Yeah, so we're kind of trying a lot of different things.
Any more questions?
Question, and a little, just the very last part of it. I was thinking like in a mountain setting, when you have a glacier. I am not an expert in this, but when I think about mountain glaciers, from what I understand, what I know is that the glacier itself interacts with the bed that it's on, like over the course of anything from seasonal time scales, a decade, or the hundreds of years, thousands of years. So the place in the mountain where the glacier forms, the bed there is impacted by essentially the quote unquote the mass that's sitting on. Is there any way you're incorporating that into the model? Because I feel like the model could be misled, because if
a colleague of mine said we have to talk to a geomorphologist, because essentially we are creating a training data set by including mountain regions that may be shaped in different times, so may contain different features. For example, erosions by rivers, which may be very different from kind of a glacier valley. And yeah, so that's one of the biggest unknowns is how do we create this training data set, whether we should in some way focus more on some specific part of mountain ranges, or make a more focused approach towards a more controlled training data creation. So I don't have any specific answer to that.
I saw a talk maybe a year ago where they presented like forward simulations of every glacier on Earth, which is a very different approach. You take boundary conditions and you actually simulate the flow of a glacier.
Yeah.
So I'm wondering how this kind of connects to what you were doing. For that kind of work, is it that, like, where are they getting their initial conditions from? Are they just plugging initial conditions from like one of these two papers and then running it forward, or are they like simulating these from scratch and actually like getting their own thickness distribution emerging from the model, or how do you put these two approaches together?
So the question was, how is this work considered by people that do for simulation essentially in the future. For what I understand, I'm not an expert on this, but for what I understand, they take either Milano and Farinotti as the initial condition for their forward simulation. So with this respect, I guess our modeling effort is one of the possible. It would be cool to model a forward simulation using different initial conditions for the ice thickness distribution and see how the results change in their forward simulation, I guess.
There are no more questions. I would like to thank our speaker one more time.
Thanks.